Hi everyone, and welcome to our video for 11.4 Limits at Infinity. The skill objectives for this particular video are 1. Evaluate limits of functions at infinity, and number 2. Find limits of sequences. Conceptual objectives are first to understand that if the limit of a function at infinity exists, that corresponds to a horizontal asymptote. And then also understand that if the limit of a sequence at infinity exists, then the sequence is a convergent sequence. And if the limit does not exist, then the sequence would be divergent. Let's talk about what it means to be a limit at infinity. Now, this is provided that this limit does exist. We're going to let f of x be a function. Then we use the following notation to represent limits at infinity, again, as long as that limit does exist. The limit as x approaches infinity of f of x equals L. What that would then mean is that we would have a horizontal asymptote. The horizontal asymptote would be y equals L, whatever L happens to be. And if we're talking about the limit as x approaches negative infinity of f of x, if that equals m, then that means that there is a horizontal asymptote of y equals m. Now again, you have to keep in mind that infinity and negative infinity are not numbers. They do not have a spot on the number line. They are used to indicate that we have just unbounded growth taking place. Also, again, remember here, this part up here, if that limit exists, it is possible that the limit as x approaches infinity or as x approaches negative infinity of a function would not exist. Now, way back in Chapter 2, when we dealt with rational functions, we talked about horizontal asymptotes. In fact, we had really this rule. This is from Chapter 2 here. In terms of a rational function, we have a rational function, which is a numerator polynomial over a denominator polynomial. And the degree of my numerator is n. The degree of the denominator is m. And what happened here, when we were looking at horizontal asymptotes, we really looked at the degree of your numerator and denominator. If n was less than m, then there was a horizontal asymptote for that rational function, and that horizontal asymptote was the x-axis, or y equals 0. If n was equal to m, then there was a horizontal asymptote, and the horizontal asymptote was just the ratio of the leading coefficient. So what we did, we looked here, again, n and m are equal, so the horizontal asymptote would just be the coefficient on x sub n, x to the n, and the coefficient of b of x to the m. So a sub n over b sub m. And then when n was greater than m, then there's no horizontal asymptote. We actually have unbounded growth. And so if we're talking about that situation, there's no horizontal asymptote. The limit would be the limit on that would end up going to infinity. So one of the things we asked you to do at that time is to look at these in terms of horizontal asymptotes. So when I look at this first one here, 6x minus 4 over 4x squared plus 1. The degree of my numerator is 1, because it's the highest power in x in the numerator is 1. Highest power in x in the denominator is 2. And so, since 1 is less than 2, since my numerator has the lowest degree, this one had a horizontal asymptote at y equals 0. And I could also say the limit as x approaches infinity of 6x minus 4 over 4x squared plus 1 would be equal to 0 as well. Looking at the second one, in this case we're dealing with 6x squared minus 4 over 4x squared plus 1. Again, on this one here, the numerator and the denominator actually have the same degree. So now we're looking at case 2. And so in that situation, there is a horizontal asymptote, and that horizontal asymptote is just going to be the ratio of those leading coefficients. So it's equal to 6 over 4, which reduces to 3 over 2. And I could then say also what this would mean is that the limit as x approaches infinity of 6x squared minus 4 over 4x squared plus 1, that is equal to 6 over 4, which is also 3 over 2. The last one we're going to look at in terms of these horizontal asymptotes, looking at in terms of the horizontal asymptote, is the 6x cubed minus 4 over 4x squared plus 1. In this case, numerator has a degree of 3, denominator has a degree of 2. And therefore, in this situation here, we said that there would be no horizontal asymptote. And what that would mean in terms of the limit is, I would say, if I was looking at the limit as x approaches infinity on this one, of the 6x cubed minus 4 over 4x squared plus 1, I would say that does not exist. Or I could say that the limit would be going towards infinity as well. It would be having unbounded growth. So that's really looking at things in terms of horizontal asymptote. The horizontal asymptote, if you look at the rational function, what would be the horizontal asymptote that we looked at in chapter 2, section 6, is actually that horizontal asymptote also represents the limit of that rational function as we go off to infinity. Now at this point, we're also going to look at ways to do this algebraically. So that from now on, I will be using algebraic techniques, but remember both of these are correct and can be used in terms of identifying that limit. What happens here is we're going to look at what are called two special limits, and really they actually represent almost the same thing. What happens here is, as I take the first one, I'm taking the limit as x approaches positive infinity of 1 over x to the n. Now what you have to keep in mind, n is a positive integer. So if I take a big number, raise it to a positive integer, I'm getting an even bigger number. And then 1 over a very, very big number, the reciprocal of a very big number, is a very small number. So in this case, I would say the limit as x approaches infinity of 1 over x to the n is equal to 0. The same thing is going to be true for x as the limit as x approaches negative infinity of 1 over x to the n. Now in that case, what's happening is I'm putting a very big negative number, a number very far from 0 in the negative direction. If I put that in for x, now raising it to a power, I'm either going to get a big positive number or a very big negative number. And regardless of how I look at it, either positive or negative, the reciprocal of a very big positive or very big negative number is going to also be a very, very big or very, very small positive or negative number. And so what happens here, the limit as x goes to infinity of 1 over x, as x goes to negative infinity of 1 over x to the n, is also going to be 0. Now we're going to use that to help us go through and algebraically find limits as we go off towards infinity. Now when working with rational functions, what we're going to do, we can always go and multiply or divide the top and bottom of a rational function by the same thing. And so what we're going to do here to go and algebraically determine these limits using that special property that 1 over x to the n, the limit of that as x goes to positive or negative infinity equals 0, we're going to use that to help us identify the limit of these things. To do that, what we're going to do is you're going to identify the highest power, the degree, the highest power on x in the denominator. So in this case, in the bottom of this fraction, I have an x cubed, x to the first, and a 1. So my highest power on x is x to the third power. And so what I'm going to do is I'm going to go through and rewrite that. And I'm going to rewrite it, I'm going to divide everything by x to the third. So when I do that, this is now going to become the limit as x approaches infinity of 4x over x to the third plus 2 over x to the third all over x cubed over x cubed minus x over x cubed plus 1 over x cubed. And what we're going to do now is we're going to simplify that. And really what that means is we're going to reduce all these fractions wherever possible. This will now be the limit as x goes to infinity of 4x over x cubed reduces to 4 over x squared plus 2 over x cubed doesn't reduce all over x cubed over x cubed is 1 minus 1 over x squared, and then the last one is plus 1 over x cubed. Now, using that properties that we just saw, we know that anything that is a constant over a power of x as we go to infinity is going to go to 0. So in this case, I know that numerator is going to be 0 plus 0 over 1 minus 0 plus 0. I get 0 over 1, which equals 0. So in this case, that limit as x approaches infinity of 4x plus 2 over x cubed minus x plus 1 is equal to 0. That you could also see that with the horizontal asymptote because the degree of the numerator is smaller than the degree of the denominator. Now let's take a look at one where where we have the degree is actually higher in the numerator than the denominator. What I'm going to do here, again, I'm going to go and identify the highest power on x in my denominator. So in this case, it's x squared. And I'm going to divide everything by x squared. So this will now become, that will equal the limit as x approaches infinity of 3x cubed over x squared plus 4x over x squared all over 2x squared over x squared minus 1 over x squared, which will equal the limit as x approaches infinity. And I reduce that, 3x cubed over x squared will become 3x plus 4x over x squared becomes 4 over x all over 2x squared is 2 minus 1 over x squared. And so as x goes to infinity in this case, I know that as x goes to infinity, 3 times infinity, that's going to be infinity, plus 4 over x, that's going to go to 0, over 2 minus 0. So I get, in this case, infinity divided by 2, which a very, an unbounded growth divided by 2 is still going to be unbounded growth. So in that case, it's going to infinity, or that limit is infinity, or I could say it does not exist. Now let's take a look at a third example where we're going through and finding this limit by going and doing it algebraically. In this case, again, we have the limit as x approaches infinity of 4x cubed minus 7x squared plus 1 over 1 plus 2x minus the 5x cubed. So again, we want to identify the highest power on x in the denominator. In this case, it is an x cubed. So what I'm going to do is I'm going to rewrite this as by dividing everything by x cubed. So this will equal the limit as x approaches infinity of 4x cubed over x cubed minus 7x squared over x cubed plus 1 over x cubed all over 1 over x cubed plus 2x over x cubed minus 5x cubed over x cubed. Simplifying that, that equals the limit as x approaches infinity of, 4x cubed over x cubed is going to be 4 minus 7 over x plus 1 over x cubed all over 1 over x cubed plus 2 over x squared minus 5. And now on this, as I remember our properties of limits, the limits as x approaches any number of a constant is just going to be that constant. And so I know this is going to equal, when I do that, the limit in terms of the top is going to be 4 minus 0 plus 0 over 0 plus 0 minus 5. So I get negative 4/5. So in this case, that limit is negative 4 over 5. So with that, you can see in both cases, in all these cases, that what was the limit actually would also be the horizontal asymptote that we saw before. So really what you're doing when you're working with a rational function, when you're trying to find that limit as you go off towards positive or negative infinity, you're really looking for that horizontal asymptote. And this is a process you can work through to do these. Now let's take a look at limits of sequences. And what you really want to do on this, you want to recall that a sequence is a function whose domain is the positive integers. So when I talk about, so for every positive n, a sub n is going to equal f of n. So we have some function where we're plugging in positive integers. And so what that means then is if the limit as x approaches infinity of f of x equals L, then that same thing is going to be true. The limit as n approaches infinity of a sub n is also equal to L. And if that limit exists, then we would say that that particular sequence converges. So one of the things they're going to ask you to do is to determine, does a sequence converge or diverge? And really when they do that, they're saying find the limit as n approaches infinity of a sub n. Well, let's look at this first one. A sub n is equal to n minus 1 factorial over n plus 1 factorial. Well, I know that that can be simplified. I know that n minus 1 factorial is smaller than n plus 1 factorial, so I know that n minus 1 factorial will be a factor of that denominator. And so I can write that as n minus 1 factorial over n plus 1 times n times n minus 1 factorial. In that case right there, this will now reduce. So I can reduce that. The n minus 1s will drop, n minus 1 factorials will drop off, and that will equal 1 over n plus 1 times n. And so to determine if that sequence converges or diverges, I need to take the limit as n approaches infinity of 1 over n plus 1 times n. Well, in that case, it's very easy to see that this is going to be that the denominator is going to grow without bound, so that limit is going to be 0. And so therefore, I would say in this case that a sub n equal to n minus 1 factorial over n plus 1 factorial. We know that sequence converges. Now let's look at the next one. A sub n is the cosine of pi n. Well, what happens on this one? Now this one's a little bit trickier, but let's look at what occurs. We're going to put different integers in for n. So when I put these in, what you have to realize is that we're going to be taking the cosine of a multiple of pi. And the cosine of a multiple of pi really goes between two values. Cosine, when I put 1 in for n, I know a sub 1, in this case, is going to be the cosine of pi, and pi times 1, which would be cosine of pi, which I know the cosine of pi is negative 1. A sub 2 is going to be the cosine of 2 pi, which is 1. A sub 3 is the cosine of 3 pi, which is going to be negative 1. A sub 4 equals the cosine of 4 pi, which is 1. A sub 5 equals the cosine of 5 pi, which is negative 1. A sub 6 is a cosine of 6 pi, which is going to be 1, and this will continue. This is a sequence that really, it's oscillating between two numbers. And so remember, one of the situations we had where a limit didn't exist is when we were oscillating, where it was just constantly oscillating between two numbers. So in this case, the limit as n approaches infinity of the cosine of pi times n, that does not exist. And so I would say that therefore this sequence diverges. This now does conclude the video for chapter 11, section 4. Make sure that you identify any questions you have in terms of the material we've looked at. We'll also talk a little bit more about some other functions that you have that you may not think of as being ones that are oscillating between two values, but we'll look at those as well. And but with that, I hope everything is going well, and I will see you at our next class.